All right, for our second reaction, we're going to talk about, again, another alkene addition reaction. And this is going to be a reaction where we add HX to an alkene. So again, the functional groups we're looking at are alkenes, and we're going to be adding our reagent HX, right? So that's a protic acid, HBr, HCl, HI is another one we could see. So we're going to be adding that to an alkene. All right, so if you look at this reaction, right, we're going to again be breaking the pi bond, adding an H and adding an X, okay? And you'll see we're going to have Markarnikov addition, and I'll describe what that means in a second. So if we take a look at this first reaction here, draw our double bond, right? We can add HBr, right? There's really two possible products we could form, right? We could add the H to the left side and the bromine to the right, right? Or we could add the bromine to the left side and then the H to the right side. So in black, this is the H that's already there. Let's draw that in. And then the new H we add is in blue. So there's two possible products that we could form. And in reality, when you run this reaction, we're going to get a major product. One of these will form in a much higher percentage, and then the other one will form in a very small percentage. Okay? So Markarnikov was a chemist who first studied this reaction. He took lots of alkenes, okay, and added protic acids to those and studied what the final products were that were formed. So he developed a rule called Markarnikov's rule. Markarnikov's rule states that with the addition of a protic acid, so HX, okay, to an alkene, the hydrogen is going to be attached to the carbon, attached to the sp2 carbon that has more hydrogen substituent groups, and the halide, our X, Br, Cl, will get attached to the carbon that has more alkyl groups on it. So another way to think about this is you can say that the hydrogen atom is added to the carbon that has the greatest number of hydrogen atoms, while the halogen is added to the carbon with the least number of hydrogens. So that's Markarnikov's rule. He studied this reaction over and over and developed this rule. So if you look at our final products here, when we have these two options, right, in this example here, there are the two sp2 carbons. So this sp2 carbon, the sp2 carbon on the left is attached to two alkyl groups, two methyls. The sp2 carbon on the right is attached to one alkyl group and one H. So Markarnikov's rule says that the H will go to the side where there's more H's, all right? So that means that this will not be the major product. That is our minor product. And in fact, the product on the right will be our major product, okay? And when I'm asking you to draw the products for these reactions, you're going to see I'm really going to be asking you to just generally draw the major product, not the minor product, all right? So if we look at the example on the left, on the top, again, this is the same example, two sp2 carbons. The carbon on the left is more substituted. It doesn't have any H's, while the one on the right does have an H. So our final product is where we add a bromine to the carbon on the left. In our next example here, again, we have two sp2 carbons. The carbon on the top is connected to two alkyl groups. The carbon at the bottom is connected to one alkyl group and an H. Therefore, we're going to add the H to the side where there's more H's, and the chlorine to the top side. And that's the final product we get here, okay? So what you see is that we're, again, breaking the pi bond, adding a hydrogen and an X, and we're following Markovnikov's rule. We're adding the halogen to the more substituted sp2 carbon. All right. So it turns out Markovnikov was just a scientist who studied this reaction. He didn't really understand why it took place, right? And to kind of dive deeper to understand how reactions take place, we really want to talk about the mechanism of the reaction. All right? So again, when we talk about mechanisms, scientists have spent years and years studying these mechanisms and looking for intermediates. All right? So Markovnikov's rule is really just an observation. The mechanism is going to tell us why it's actually true. All right, so let's take a look at the mechanism of this reaction here. So let me clean this up, and then I'm going to show you how to do the mechanism, right, for our top example here. So we'll take this alkene, right, and I'm just going to draw in this hydrogen so it's clear. We're going to add HBr to this reaction, our protic acid, and we already know what the product we're going to get out is. Right, we're going to add a bromine to this side. Okay, so that would be our final product. If you wanted to show the hydrogens around the sp2 carbon, right, we could do that. There's one in black that's already there. Blue, there's the new hydrogen, and then there the bromine, right? So here I'm just focusing on the hydrogens around the alkene. So let's take a look at the mechanism on how this works, all right? So if you remember, when we have HBr, that is a strong acid, which means it's going to completely dissociate. So if you add HBr, right, that means we're going to have a solution of H plus and Br minus. Okay, that will completely dissociate, all right? And it turns out in the mechanism, what's going to happen is these two electrons in the pi bond, the two electrons of the pi bond are going to break. That is a weak bond. So remember, between these sp2 carbons here, I'm sharing 4 electrons, one from the sigma and one from the pi. Just the 2 electrons from the pi bond are going to break, and they are going to attack and form a new bond to the hydrogen. Okay? So it turns out there's 2 possible scenarios. I could add the hydrogen to the left side or the hydrogen to the right side. Now we know the answer is going to be we add it to the right side, but let's see why. So I can add the hydrogen to the right side, which leaves me now with a carbon that only has 3 bonds. So if you remember from formal charge, that carbon therefore has a plus charge. Or, right, we can add the hydrogen. So we can add the hydrogen to the right side, or we can add the hydrogen to the left side. Again, now the carbon on the right only has 3 bonds, and that carbon would have a positive charge. Okay, so there's really 2 options here, right? We can add the hydrogen to the right and get this carbocation here, or we can add the hydrogen to the left and get that carbocation there, all right? So we know that this is going to be the correct way because we can look at our product, right? Our product knows we follow Markovnikov's rule, so we know that's the right answer. But the question is why? Why is this, why do we go through the intermediate on the left versus the intermediate on the right? To understand that, we have to learn a new concept called carbo-cation stability, right? Why would we form this carbocation instead of that one? Well, the answer is simple. The carbocation on the left is more stable, right? So the carbocation on the left is more stable. And it turns out carbocation stability is pretty simple. A tertiary carbocation is going to be more stable than a secondary carbocation, which is therefore more stable than a primary carbocation, right? So what's a tertiary carbocation? A tertiary carbocation is when you have a carbon that's connected to 3 other carbons, okay? So I'm using the letter R here, I'm using the letter R to represent carbon atoms. Okay, so R really represents carbon atoms. So we have 3 carbon atoms surrounding our carbocation. That's the most stable carbocation we can form. That is more stable than a secondary. A secondary carbocation is when you have a carbon attached to 2 carbons and 1 hydrogen. So there's a secondary carbocation. And a primary carbocation is when you have a carbon attached to 2 hydrogens and only 1 other carbon. That's a primary, okay? And what we know is that a tertiary carbocation is more stable than a secondary, which is more stable than a primary, right? And these are obviously more stable than just a methyl carbocation, and we're really not going to see many of these, okay? So let's go back and look, what type of carbocation do we have? So if we look at this carbon in green, it's attached to 1, 2, 3 carbons. That is a tertiary carbocation. What about the carbocation on the right? This is attached to 1, 2 carbons and 1 H. Therefore, that is a secondary carbocation. So we know, right, that this tertiary carbocation is more stable. So we are going to tend to form this carbocation, right, in a much greater amount, a much greater yield than that one. So we can basically ignore this because we're really not going to form it. Okay, we're really not going to form it. So let's clean this up a little bit so we can finish the mechanism. All right, so I'm just going to erase here. So if we go back to our mechanism, right, we know we're going to add the H to the side where there's more H's, not because Markovnikov tells us, right, but because we're forming a more stable carbocation, a tertiary carbocation. So the first step in our mechanism, we can call this a protonate because we're adding a proton. So I'm writing the letter P. Then what's the next step in the mechanism? It's very simple, right? This bromine is now going to attack that carbon, right? This carbon has a plus, this has a minus. This lone pair here is going to form a new bond. And we can call that an attack step. So the mechanism is really easy. We are going to protonate, show this arrow here, draw our intermediate, and then the lone pair and the bromine will attack to form our final product. So that is the mechanism of this reaction. All right, pretty straightforward, pretty simple. Let's just do it one more time. Let's look at the example on top. Okay, so I'll come over here. So if we draw this molecule here, we have an alkene. We're going to treat this with HCl. Okay, so we already know what the product's going to be, right? We're going to follow Markovnikov's rule. So we're going to add the chlorine to the side of the double bond where there's less hydrogens. All right. So if we draw out our mechanism, HCl will completely dissociate to form H plus and Cl minus. Our first step in the mechanism is a protonate. The pi bond is going to attack and form a new bond to this H. right? So there's a hydrogen here, hydrogen here. Here's our new bond in orange. That's a new bond to our H. And consequently, we have now formed a tertiary carbocation. Next step in the mechanism is our chlorine is going to attack. So sorry, first step is protonate. Our second step is to attack. This chlorine will form a new bond to that carbon. So there's our new bond here. All right. A couple terms I want you to be familiar with, right? When I use this term attack, right, and this is a term I use to help students. It's not a formal term used by organic chemists. The species that has electrons and is forming the new bond is called the nucleophile. So here the chloride anion is our nucleophile. And the species that gets attacked, right, is called the electrophile. Okay, so these are two terms we need to know. The Cl- is attacking the carbocation. So the Cl- is our nucleophile, and the carbocation is our electrophile. Okay, so this is the reaction and mechanism for HX addition.